I'm John, and today we'll be talking about elastic silicon interfaces. Or meet your robot plumber. He's got a tiny soldering iron and knows how to use it. You've been tasked with writing a data compression accelerator. You spec out your design and hand those specs off to the software engineer. 2 weeks of hacking later, and you've got your compression core. Congratulations. The software dev comes back with something ready to test and asks for working hardware. You send her a copy of your IP block, and she kind of tilts her head to the side and asks, "What is this?" You realize you forgot the rest of the system. I'm going to need a minute. 2 weeks later, you have a fully complete design. You sheepishly request the software from your peer. You load your code on your FPGA, run the software, and the bits start to flow, but the bits are gibberish. You call a meeting with the software dev, and after some heated words and a lot of debugging, you both discover an endianness issue. And there's an off by 1 cycle error in your compression core's host interface adapter, which you hurriedly wrote while strung out on Red Bull. Not surprisingly, a robot plumber would have come in handy. ESI is an interconnect compiler which is based on strongly typed, latency and sensitive communication. These properties yield several features which would have helped this admittedly bombastic fictional situation. First, your software peer and you could have co-developed the system using co-simulation, a link from real software into the simulation world. ESI creates a software API to develop against, a hardware interface to design to, and a bridge from her software to your simulation, enabling your team to catch bugs sooner. Since ESI handles things like endianness automatically, based on the types it knows about, that bug, depending on where it was, could have been avoided completely. Likewise, since that off by 1 cycle error was in your adapter code, it would not have even been created since ESI synthesizes adapters for you. Getting back to our parable, your data compression accelerator has been so successful it is now deployed at some scale. Your insane boss, however, wants a question answered. How often is your compressor compressing the byte sequence bad cafe? Presumably since he wants to get a feeling for how often people are writing about bad coffee? Regardless of the reason, this is easy to do, even in Verilog. And knowing your boss will likely change his mind and ask for 8 bad food after he gets food poisoning, you decide to make your telemetry unit configurable at runtime. It would support multiple slots with variable length keys, maybe trinary search terms. It'd be the Rolls Royce of stupid telemetry. But then you realize that while the unit itself is easy to write, even in Verilog, you have to get the counter value out to software. Worse yet, you need a control path to install keywords in your over-designed, pain-in-the-neck telemetry unit. But you learned your lesson the first time and consulted a professional plumber. ESI will have the capability to automatically multiplex data streams using its planned services feature. In this case, the configuration could be hooked into a control plane config service with all the other components that need to be configured. Similarly, the counters connect to a telemetry service with all the other telemetry units on the device. These services themselves would be backed by a PCIe service along with the uncompressed and compressed data streams. Based on the data types, ESI would create a specialized software API for each service's clients. For example, the search term config API could be a memory mapped array of search terms. When software writes to a search term field, ESI would then route the configuration command accordingly and update the proper search term. Your boss, being kind of reasonable for a change, asks for a new feature. Implement a new AI-assisted compression core. Because everything is a little better with deep learning, and who cares about bit accuracy anyway? I may have spoken a little too soon regarding reasonable. You find an NPU which you hope to treat as a black box. It speaks AXI, you know AXI, this'll be easy. You spend some time hooking it up, and it works. Kind of. You see traffic, but your accelerator isn't getting the same results as the software model. You bash your head against your desk for a few days, then discover the issue. You correctly implemented the AXI protocol, but one of your components was misinterpreting the data on the untyped AXI bus. It is 6-bit packed neuron weights, not 8 in this configuration, you moron. That was specified in the documentation. Again, ESI would have prevented or caught this bug. Since strong static typing is a key feature, 6-bit versus 8-bit would have been trivially caught. Untyped buses, like AXI, are an implementation detail which ESI abstracts away. Data types are modeled logically, then large structure arrays can optionally be scheduled over multiple cycles. For instance, the NPU configuration could have been a single struct containing both the global configuration and all the weights. Said struct would clearly be too large to transmit in one cycle, so ESI allows designers to schedule the communication, breaking up the large struct over many cycles. Sick of your boss, you transfer and found a new team responsible for the same device. Your organization leader, however, has a reputation for overpromising features and under-resourcing projects. At first, your team is only asked for one small feature, a data encryption core, to go after the compression core. Midway through that work, you're asked for a data decryption core. Your team has no choice but to rush through the encryption core, doing a horribly inefficient job to get to the decryption core. Decompression, same story. Then comes the final straw. Your company, convinced there's more money to squeeze out of the FPGA in your team, wants you to add a Bitcoin miner. Exasperated, you reluctantly begin looking at so-called high-level hardware description languages. You can use them to meet schedule and, as a bonus, waste a bunch of area so your team doesn't get asked for further features. There's one guy in your team who always talks about HLS. There's always one. So now's his chance. He comes back after only a week with something that works. You had heard that high-level design was more productive, but only a week? More surprisingly, the core was high performance and smaller than the wasteful mess you had expected, and frankly, the rushed system Verilog you and your team generally produce. But there's a catch. The core was designed in a proprietary environment which made the external connectivity super easy, but only if you were to let their technology control your device, their technology control your build. Worse yet, the positive results had you so excited that you began looking to other technologies, some of which, out of the box, required their own bespoke runtime stack. You really want to port all of your existing, hastily written code to more appropriate languages, but the integration would be a real challenge unless you moved everything over to one environment, tying yourself to that environment's vendor. You start to hang your head in shame at the state of composability and hardware design, but then you remember your friendly robot plumber. This use case was the original motivation for ESI. In an ESI world, HDLs would only be responsible for their own block, and ESI would be used for all communication. A high-level standardized type system would allow any ESI-compatible language to talk to each other, much like the .NET type system. ESI would act like a software linker, connecting all the blocks to each other and the host system. A few of the potential benefits are listed here. As you can see, few are done. In order to realize ESI's aspirations, we need community involvement. As such, ESI is part of the Circuit project, which you'll probably hear about in the keynote. Thanks for listening, good night, and please tip your plumbers.